the kind introduction and also for the invite, and also my extended regards to Professor Manoj. And today's topic is about fundamental limits of photo detection at quantum level. So let me first give you a brief introduction about quantum. So I hope you remember we all have studied classical optics, and you see on the y-axis we have size, and on the x-axis we have intensity. So classical optics is a subject which has bigger sizes and higher in terms of intensity. So for example, if you look at the lenses, what we use, they comes generally into the classical optics domain. The another domain is nanophotonics, where we have lower size, but intensity remains high. For example, you have plasmonic nanoparticles. They are smaller in size, but we deal with normal light. Then comes the quantum optics, where the intensity of light reduces drastically, but sizes still remains bigger. For example, we have nonlinear crystals, BBO crystals, which we use to make single photon sources. There we use bulky optics, but we are dealing in terms of very low intensity picowatt. And in future, there might be a domain where we will go into quantum nanophotonics. So we will reduce the size as well as intensity. So first, before we start the limit of these photo detection, let me give you a brief idea about photon statistics. So it's possible that you might have already know about this topic, but still this is the very core of this detection limit. So I would like to explain you a bit. So suppose we have a light beam. In front of a light beam, we have a photomultiplier tube, or let's say an avalanche photodiode, some sort of diode we have placed in front of the beam. And then we have a counter. What this counter does is that whenever a photon hits the diode, it will start showing you the signals. So this is the signal when one photon hits, then when second photon hits the second signal, and then third and fourth, like that. So suppose we have a system like this, and I give you the wavelength, which is 620 nanometer, and energy is 2 eV, and power of this beam is 1 milliwatt. So I have given you some parameters related to this beam, and as you know that you can now calculate the number of photons. So since power is n into h mu, or nhc by lambda, you know everything here. You know the power which is given, you know the lambda which is given, c is the velocity of light, h is Planck constant. You can calculate what is the number of photons. So if you try to calculate average number of photons, or we can also call it the photon flux, it comes out roughly 10 to the power 15 per second. So I just want to give you a rough estimate how many numbers of photons coming per second. So this power 1 milliwatt is roughly a normal laser pointer, what we have when we give presentations. And this laser pointer in 1 second is giving 10 to the power 15 photons. Okay. So can we now understand the quantum properties of this laser pointer? The answer is no. But why we can't do that? So the reason is the dead time of the detector. So what is the dead time of the detector? Is the time up to which the detector cannot detect anything. So usually the detectors have their dead time in microseconds or nanoseconds. So the best detectors available on Thor Labs, normal avalanche photodiode, you go to Thor Labs, if you purchase something, they have 10 nanoseconds of dead time. Now, just please remember that in 1 second, 10 to the power 15 photons coming. Okay, now I will tell you why I am talking about the dead time. So let's say we have a detector, and this is the response of our detector. What do I mean by the response? Meaning the detector is off for 1 microsecond, which was the dead time, meaning if a photon comes in a shorter time interval than a microsecond, let's say a nanosecond, the detector cannot detect it. and then the detector is on for some time and then off again for 1 microsecond. So the question is, how many photons, the maximum number of photons this detector can detect in 1 second? This we want to know because we already know that we have a laser source which is giving 10 to the power 15 photons per second. Now we want to know what the detector can do, how much it can detect. So let's say this much distance here to here is 1 second, right? Now let's say one photon comes, the detector will detect it, and then detector will sleep for 1 microsecond. Next photon comes, it will detect again, and then it will sleep again. And then the third photon comes and the fourth. So if you do this, you will find out that maximum number of photons which can be detected is 10 to the power 6 in 1 second. But how many were coming? So 10 to the power 15 photons were coming. So we have a problem here. That number of photons which are coming is quite high as compared to the detector which it can detect is only 10 to the power 6 in 1 second. So for 1 milliwatt of power, I told you 10 to the power 15 coming, but let's say we try to reduce the power. So now I reduce the power from milliwatt to picowatt. Milli is 10 to the power minus 3, pico is 10 to the power minus 12 watts. So I reduce the power too much. And now I have a photon flux roughly 10 to the power 6 range. So I know one thing that, okay, if I want to use my detectors, I need to reduce the energy or the power of my laser source. The another option which I can do is I can make
There is some connection issue at Dr. Vaibhav end, and he is joining soon, maybe within a minute.
Hello, can you hear me?
Yes,
Sorry.
but maybe around 4 minutes back, your connection is lost. So,
Okay, let me share again.
sure.
Can you see my screen now?
Yes, it is visible. Perfect.
Okay, maybe I will start with slide number 2. Um, so I hope up to here it was covered.
Yes, please.
So yeah, again, what we would like to know is the photon statistics. That is very important before doing any kind of detector limitation or noise detection. This is very important to know what is the photon statistics. So I will just give you a brief introduction. So suppose we have a light beam, and this light beam is hitting on a avalanche photodiode or on a photomultiplier tube, and then we have connected a counter. This is some electronic machine. What this machine does is that whenever we hit with the incident photon, the machine will convert that photon into electrical signal, and then it will give some sort of response. So suppose here we detect one photon, then second, then after some time we detected third photon. So suppose I have a light beam which has a wavelength of 620 and energy of 2 eV, and the power is 1 milliwatt. So I can actually calculate the number of photons, how many photons I have per second in this beam. So since power is n into h mu, I can find out n. So the average number of photon is roughly 10 to the power 15 in 1 second in this laser beam. This kind of 620 wavelength laser is roughly a laser pointer which we use to give presentations, right? And if that is having a 10 to the power 15 photons, then can we find out the quantum property of this laser pointer? The answer is no. But why? Because every detector has some sort of dead time associated with it. And roughly the detectors have dead time usually microseconds. Some good detectors available on Thor Labs, they have nanosecond dead time. So what is the dead time? Dead time is the time up to which the detector cannot detect any photon. So for example, we have a detector which has this kind of response, and let's say for 1 microsecond the detector is off, then it remains off, and then again for 1 microsecond the detector is off, and then it keeps doing it. So how many maximum number of photon it can detect in 1 second? So in 1 second, if you want to find out, let's say this is 1 second, this complete length. So when first photon hits, after that for 1 microsecond, the detector will be off. And then the second photon comes, and then the detector will be off again, and then third come, fourth come. So you will see that the total maximum number of photons will be 10 to the power 6 for a detector which has a dead time of microsecond. But the number of photons which were coming to us in 1 second was 10 to the power 15. So it is very difficult to detect these many photons with such kind of detectors. So that is one problem. Now, how to solve it? So we can actually reduce the energy or the power. So rather than milliwatt, we go to picowatt, 10 to the power minus 12 watt. And then we have roughly 10 to the power 6 photons per second. And now at least we can deal with them with the same detector. So one way is to reduce power. The second way is to use a pulse laser. So what is a pulse laser? Let's say the red color is a continuous wave laser. This is time, this is intensity. So intensity is constant for a CW laser. But for a pulse laser, we have some on time, then it will be off for some particular time, and then it will be on again. So there is something called on time. Then the repetition rate, meaning after this much of time length, the signal comes again, and then you can convert it in terms of frequency. Then fluence is the total number of or total power which is in one particular pulse, that is called the fluence. So let's now take a question. Suppose we have a pulse laser which has a wavelength 800, power is 1 milliwatt. It repeats itself every 100 megahertz, meaning every 10 nanosecond you can convert frequency into time. So every 10 nanosecond the pulse is coming. Now if I calculate the number of photons in this pulse laser, in each pulse I will be having 10 to the power 7 photons. So that is another way to get less number of photons. So there are two things you can do. Either you can cut down in terms of intensity, or you can cut down in terms of time, or meaning creating pulses. So there are two ways. Now let's take one more example. Suppose we have one EV energy light which has a power of 1 nanowatt, and this light hits on a photodetector, and this detector has a efficiency of 100%, meaning all the photons converted into the current. Now we would like to know how many average number of photons are there in a beam segment of 30 centimeter. So as you know, we know here, we know the power, we know the energy, so we can calculate N, and we know, okay, we have 6.25 10 to the power 9 photons per second. So in 1 second, if we have this much of photon, then in 1 nanosecond, you just multiply 10 to the power minus 9 both sides, and we now know that in 1 nanosecond, we have 6.25 photons. So how long is 1 nanosecond in terms of length for a photon? So we know that the velocity of light is 10 to the power 8 meter per second. So in 1 second, light travels this much of distance. So in 1 nanosecond, light or photon travels this much of distance, which is 30 centimeter. And this was the question, that in 30 centimeter, average number of photons. So 30 centimeter is equal to 1 nanosecond. If I know the photons in 1 nanosecond, I can tell. So I know that already in 1 nanosecond, there are 6.25 photons. So in a 30 centimeter length, I have 6.25 photons. Remember that photon is quantized number. It can only be integer 0, 1, 2, 3, 4. 6.25 is average number. Now, suppose rather than one EV, if I have a two EV light source. So average number of photon will go down by 2. You just have to divide the energy. So it will be 3. And I told you photon is a quantized number. So whenever I say 3.1, meaning uh, when I'm showing 3 photons, it's just approximation. So now we have this 30 centimeter of line segment, and what I want to do is, and I want to take a picture of this line segment with a very high speed camera. So this camera is very high speed, meaning it can take pictures every nanosecond. It can keep clicking pictures. So let's take the first picture. I knew that average number of photon is 3.1. I took the first picture. It was a 30 centimeter long line segment. I found 3 photons. Okay, this was my first picture. Then again I took second picture. I did not find anything. Then I took the third image. I found 4 photons. And then I kept taking. So I found 5 photons, then 4 photons, then 5, then 3, then 2, and then again 3. And then the last picture, I took 10 images. So in the 10th one, I found again 2 photons. So if you take sum of this 3 plus 0 plus 4 plus 5, all that, divide by 10, you will find out 3.1. So remember, when we are saying we have a 3.1 photons, they are average number of photons. So I hope that is clear up to now. Now I want to reduce this length. So rather than 30 centimeter, I want to go to 3 centimeter. So now I have 3 centimeter. And if you do that, you will have average number of photon, which is 0.31. What does it mean? 0.31 average number of photon. So suppose this time I take even more high speed camera, which is 100 picoseconds, and it's taking pictures. So I take 10 pictures again. In the first picture, I don't find any photon, then I find one, then nothing, then I find one again, and then 0, like this. So what is actually happening, that out of 10 measurements, only in 3 occasions I found something. And if I take the average of this, it will come out 0.31. Let's take one more example. Again, I kept everything same, but I reduced the uh, or I increased the speed of the camera, how fast it can take pictures. Now it's taking 1 picosecond. And let's say average number of photon is now 0.031. What does it mean? It means that out of 1,000 measurements, so 1,000 pulses are coming, and you are able to detect photons only in 3 pulses. So here you had 10 pulses. Out of that 10 occasions, there were only 3 occasions where you found something, meaning there were some photons available. And in this case, out of 1,000 pulses, only in 3 pulses you will find photons, right? Now there is a very basic question or intuition should come in my mind. Suppose I have this 30 centimeter length, right? And I can detect photons. I have very high speed camera, all that. But still I don't know at what time these photons are there and where are they. So there are two questions: where and at what time. So for example, let's say there is this laser and the photons are keep coming from this laser source, and I take a 30 centimeter segment and I click a picture. At one particular instant I find 3 photons and they were here. Second picture I clicked, and then I found the 3 photons were there, like this. And then I took another images. Sometimes I find them like this, sometimes I find them like this. So now I am not able to understand that, okay, how they are distributed. So the answer is that photon detection is random in nature itself. So why this happens? So remember, lasers, actually how lasing happens. Lasing happens because of, let's say, related light emission, right? And there is some gain medium inside the laser. What is that gain medium? That would be some semiconducting material in semiconductor lasers. What is that semiconductor? It has some valence band, it has some conduction band. And what we do is that we do first excite this gain medium. So we hit with some photon, and this photon energy is transferred to this electron. This electron goes up and then it comes down. That is the basic spontaneous emission process, right? But when the electron goes to conduction band, every of these energy bands, they have also lifetime associated with it. So let's say if lifetime is 10 nanosecond, we cannot tell. So lifetime 10 nanosecond, meaning the electron can stay here maximum for 10 nanoseconds. But when will it come down? That we don't know. Maybe it is possible that it goes up and then within 1 nanosecond it comes down, or maybe in 2.5 nanoseconds it comes down, or maybe in 8 nanoseconds. That process itself is random in nature. And this creates all the randomness, which is again coming through lasers and this photon statistics. So that is the main cause. So as I told you, we are not sure what is the distribution of these three photons of in 30 centimeter length, because we knew that average number of photons were 3 point something. And if we take different pictures, in some image we have 0, some image we have 3, 5 something, but we still don't know what is the real distribution, right? So let's say again we have a laser, and this laser has some power, right? And what is the number of photons? We can divide this power by h mu. We find the number of photons. Now we take a length of L, and we try to find out number of photons in this L length. So you already know that light travels c into 10 to the power 8 meters in 1 second, meaning light travels, you can also call it c, the velocity of light or the constant c. So light travels c distance in 1 second. So in 1 second, number of photons is equals to 5, which is the photon flux. And in length c, number of photons is also equal to 5, right? So how much photon will be in length L? That will be 5 divided by c into L. So average number of photons is pi L by c. That would be your average number of photons. This is what we are doing up to now. I just showed you many examples. Now I'm just generalizing it. So now suppose I divide this whole length by different small segments. Let's say n segments. And now I want to know what is the probability of finding a photon in one of those segments. So I know the average number of photons is n bar. And if I divide it by the total number of segments, this will be the probability. But that is the probability to find one photon. What is the probability of finding n number of photons in that beam segment? So for example, you remember this example, right? So we knew average number of photons is 3.1. And we wanted to know what is the probability of finding 5 photons in a beam segment of 30 centimeter. What is the probability of finding 0 photon in a beam segment of 30 centimeter? What is the probability of finding 2 photons? So you know what we were doing here. We are just trying to figure it out, the formula, how this distribution is there, like how are they distributed in a particular manner or not. So if you do that, you will find out that the probability of finding n photons in the beam segment, it comes out like this. That is the formula. P is the probability, n is the number of photons, 2 photons, 0 photon, 1 photon, and this is the formula. Now, if n, which is so you had this length L, you divided it into n segment. If I increase the number of segments, meaning I am taking very small time intervals. So I'm taking many shots like 10 nanoseconds, now picoseconds. So I'm reducing time in a very short interval. That is the meaning of increasing number of number of segments. And if I do that, then finding n number of photon will come out something like this to find out n number of photons. And people call it Poissonian distribution. So actually, this is not something random. It has some sort of dependency or probability distribution, which is called Poissonian distribution. And here the n is a number of photons, which is integer. So how this Poissonian distribution looks like? So if the formula is like this, then this is how these distributions looks like. Okay, let's talk about this particular distribution. So in the x-axis, we have number of photons. On the y-axis, we have the probability. N bar, average number of photon is 1, right? So average number of photon is 1, like you remember 3.12 and all that. So that is n bar, that is equals to 1. So it is possible that 0 photon is there, or 5 photon is there, 2 photon is there, 1 photon is there. But overall, when you take the average, you divide, and then finally it should come out as 1. Now we have this formula. Look to this formula. Let's say n bar equals to 1. So we consider this case. And we try to find out P0. What is P0? P0 is the probability of finding 0 photon. What will be the probability of finding 0 photon? So we know that n is 0, which is given. So you just put n0. 0 factorial is 1. And n bar, we knew that that is also 1. So e to the power minus 1. And this n bar is 1. So 1 to the power whatever is 1. So this will come out 1 by e. So probability of finding 0 is 1 by e. So this is given here. Probability of finding 0 is here, given here, right? Now probability of finding 1 photon will, again, you can solve this. It will come out 1 by e. Then probability of finding 2 photon is 1 by 2e, then 1 by 6e. And this is what you see here as well. As soon as you go in the x-axis, you start increasing, okay, find probability of finding 0, then 1, then 2, then 4, then 5. You see that it decays very quickly. So probability of finding 4, 5, or 10 photons will soon approach towards 0. So that's how you read these Poissonian distribution diagram. You also will see that as soon as average number increases, let's say for 10, this distribution looks a bit like Gaussian. But for a small number of average photons, it is not Gaussian, it is Poissonian distribution. Now, there is something interesting in Poissonian distribution is that the center of this distribution will be equal to n bar. So it is always around n bar. So this distribution, you could also see that if you try to make it like this, it will be, the center will be somewhere close to 0.1. And the variance, this distance, how much it is distributed, that is root of n bar. So under root of 0.1 or root of 1 or root of 10. That is the fluctuation in the number of photons. That is the basic principle of Poissonian distribution. Now, depending on these distribution, actually we can also classify the light. We can say different type of lights depending on these distribution. So you can see here, here's the probability, here's the number of photons, and here we have defined 3 terms: Poissonian, which is this one, then sub-Poissonian, which goes up and a bit narrow, and then super Poissonian. And this graph is done for average number of photon of 100, and here is the probabilities. So a Poissonian light source is the one which follows this particular statistics. What is it? That the average number of photon, if you take the under root of that, that should be equal to your noise or variance or fluctuation. That is called the Poissonian light sources. What is Poissonian light source in real life? Laser is an example of Poissonian light sources, or any other coherent light source. They show Poissonian statistics. The another one is super Poissonian light sources. So the one which are like this one. So there the fluctuations are quite big actually. Fluctuations are bigger than the root of average. And who shows kind of distribution? So usually thermal light sources, incoherent light source, LED bulb, incandescent light, all these, sun, they all show these kind of distribution. And actually, they don't follow Poissonian distribution. They follow something called Bose-Einstein distribution. So those are super Poissonian light sources. Then comes sub-Poissonian light sources. So these are very special light sources. First of all, they are not classical light sources. There is no classical analog available to that. And they are called quantum light sources, and they show sub-Poissonian. So this particular statistics where the fluctuations are quite small. So the fluctuation is less than the root of average number. And these are called sub-Poissonian light sources. So now you understand that classical light, they follow Poissonian distribution. That is the crux. That is the gist of this, that classical light, they follow Poissonian distribution, meaning the fluctuation or the variance, the FWHM, full width, mini, half minima of this peak, if you take that roughly, then this will be equal to taking the root of the average number of photons. So under root of 100 is 10. These are all called coherent light sources, classical light sources, which are available in microscopes, lasers. So lasers are mostly these Poissonian ones, and super Poissonian also you use LED lamps and all that. On behalf of distribution of photons, we can also divide them. So I told you this sub-Poissonian light source, they are also called anti-bunched light source. What does it mean? These are all photon. So this is first photon, second photon, third photon, fourth. And there is no fluctuation. If you see, this is the ideal single photon source. This is quantum light sources. And you can achieve these kind of light sources using quantum dots or 2D materials or NV centers. And you will see that there is no fluctuation. Every another photon is equally spaced. Once you go to coherent light sources, for example, laser, you will see that some sort of randomness is there. So they are not equally spaced, and these kind of light sources are called coherent light sources or laser light sources. And when I say it's random, it's not random distribution, they have a Poissonian distribution. And the last one is bunched light source, and they are incoherent light sources like thermal light source, LEDs, all that. So based on the distribution, they are divided, light sources are divided into different categories, 3 categories. Also how the photons are separated from each other, they are also divided into different categories. So now remember the last lecture on photodiodes. So this was the basic structure of a semiconductor photodiode, that we have a PN junction. P is with the negative terminal and N is with positive terminal of the battery. This is called reverse bias PN junction. And here we have this depletion region, and we hit it with photons. So usually in experiments, we use lasers or we use LEDs. This is the typical sources, classical light sources, which is available to us. And I just told you that lasers are coherent light sources, but their photons comes randomly, and this randomness is Poissonian distribution. If we go to LEDs, that is also random, it's a bunched light, and the photons also come with some randomness, which is even more broader than the coherent light sources. So all the available classical light sources, they have some sort of randomness associated with them. Um, so suppose here when the photon hits, if we use coherent light source or bunch light source, this is what happens. So let's say on x-axis we have time, here we have photons. So since it is a coherent or bunch light source, we will be having a distribution in photons which is not equally spaced. So they will not be equally spaced, there will be some randomness. Now these photons will hit here on this junction. It is possible that not all the photons will get converted into electron and hole pair, and even they might be converted into electron hole pair, but it is possible that they will not contribute to the current. So what happens if you see the photoelectrons, that maybe it's possible that this photon, it created electron hole pair, but this was just went into thermal energy, lattice vibration. Also it's possible, let's say this photon also did not convert and come back into the signal in terms of current. So there will be, so see this photon absorption process itself also random. You don't know which photon out of all of this, let's say they all get absorbed, but even after that, maybe it's possible that the electron hole pair associated with this one will not give rise into some sort of current. Maybe it's possible that the electron and hole try to come out, but they do a lot of collisions inside this crystal and then they lose their energy in terms of heat. So this process itself is again random. So the first randomness came due to Poissonian statistics, but again, the photo detection process where the absorption is happening, then the photo generation, these things also gives the randomness. So let's say once the photoelectron generated, each photoelectron is giving some current pulses. So let's say corresponding to each electron hole pair generated, you are getting some current pulses, right? But this current, remember, has fluctuation due to the photon fluctuation. So the photon which is coming itself has some Poissonian distribution. Let's say the photon came, then for some time nothing came, and suddenly two came. Then nothing came for even longer time, and then one came. So this is a Poissonian distribution. And because of that distribution, definitely the photoelectron generated will have again some sort of distribution. And that is the main reason to have short noise into the photodetectors or into the system. So how the current will look like. So if you look at the current versus time, this is how the average current value will look like. Something like this, some fluctuation. It has some average value, and surrounding that average value, there will be some delta I, which is the fluctuation. So at higher frequencies, we usually have short noises, and this short noise power is given by this particular formula where you depend on the I, and this I is depending on the number of photons coming, which is already fluctuating. So your short noise also has fluctuation. This is what you see here. And you can find out the average short noise power. So here is the graph, how noise in y-axis depends in terms of frequency. So at lower frequency, you will see there will be a lot of classical noises. This might be due to some sort of vibration and all that, like flicker noise is also 1 by f dependent. So lower the frequency, higher is the noise. But as soon as you increase frequency, you will see that other classical noises you get rid of them, but the short noise is still there because this noise is because of the photon statistics, how the photons are hitting the photodetector, and then this tau d is the detector time. So at certain frequency, the detector will also stop responding, but you will still see that the short noise remains there. So you can see that this short noise power is actually directly dependent on the average number of photon square root, which is the fluctuation in the number of photon, and this is the characteristic of the Poissonian light source. So this is basically what people call the classical or quantum limit of detection. So if you see this short noise, the signal to noise ratio. Suppose n number of photons coming, then the fluctuation will be root n, average number of photons, and you take the under root of that. So the total signal to noise ratio will be root n. And this will be the case for Poissonian light sources, that you have this short noise system which has this much of signal to noise ratio. It comes due to the photon statistics, and all the classical detectors have this limit, and this is called standard quantum limit. Um, so let me just give you a brief idea, like how this creates a problem. So here I have number of photons. which is coming, and here I will calculate the short noise. So let's say 1000 photons coming, average number of photons. You take the root of that, that is 33. So for 1000 photons, a noise of 33 is okay. But if I reduce the number of photons, let's say 100 photons, I have short noise which is equal to 10. For 10, I have noise 3.3. So you see, when I'm reducing the number of photons, the noise is getting dominated. Like 33 was nothing as compared to 1000. You can divide 33 by 1000, you will find out something 0.033. But as soon as you go here, you divide it by 10, you will see 0.3, not 0.033. So suddenly you see, for a small number of photons, the short noise is getting very dominated. And I already told you, when we have to work with quantum, we have to go with less number of photons, lower intensities, higher frequencies. So we have to deal with the short noise somehow. So the first lecture is kind of dedicated towards this short noise, which I hope you might have understood a bit, that the short noise is very significant when we go into the quantum systems or low intensity systems or less number of photon systems. So, for example, if you have a coherent light, let's say laser, or even if you have sub-Poissonian like LEDs and all, if you build a detector which is 100% efficient, and this detector has zero dark noise, there is no dark current, meaning when you switch off everything and then also you have some sort of current, there is no dark current. Also, let's say you cool it down, there is no thermal noise and all that, no electronic noise, but still you cannot predict when the next photon will come. That statistics, that arrival of photon, that is the intrinsic nature of the semiconducting material and the light itself. So this gives rise to this short noise. And now we have to find out ways how to deal with that and how to go below the short noise, and what should we do so that we can measure below the short noise limit. So that will be to this will we will go deeper in the next lecture, that what should we do and how should we go below the short noise limit. So with this, I will stop this lecture here. We can take some questions, and also after that we can take a 5 minutes of break. So if you have any questions, please write in the chat. Okay, I see one question is, how is bunching of photon is done like physically or in real life. So let me just give you one example. Let's say somehow if you can take one single quantum dot and you pump this quantum dot with 400 nanometer laser, and suppose that this quantum dot emits light at 600 nanometer. Now this quantum dot, you can calculate the G2 function of this quantum dot, and if G2 function goes towards 0, this is a property that you have a single photon source, and if it is a single photon source, that means that it has a bunched quantum dots, or it has anti-bunching. So what people usually do is that they use a technique called heralding or heralded photons. So what you have to do is you have to tell your so you use two laser beams. One laser beam tells the quantum dot that now you have to emit, so you provide some sort of a trigger, and that once that trigger happens, then the quantum dot emits the photon. So by doing that, it is not one to one, like not very instantaneous, but somehow you will find out that now the spontaneous decay will not happen. At least you have a way. So your heralded photon is somehow entangled with your pump laser. So you take one path of the pump laser, you attach it with your detection device, and this tells you that, okay, now I have given one pulse to quantum dot. Similarly, it also tells your detection device that, okay, now I have given you also the one pulse. So the detection device now knows that one pulse has gone to the quantum dot. That means now whatever photon will come, that will be heralded photon. And by doing that heralding, they can actually calculate or get these bunch light sources. So then this triggering happens like deterministically. It will not be then probabilistic nature. So there are ways to make light deterministic. I hope, I mean, this is again a complete topic, but I hope I try to answer it. How one photon is defined in measuring? Is it just wave number? So actually there is a process called Hugo Mundell or sorry Henry HBT interferometer, Henry Brown and Twist interferometer. How one photon defined in measuring? So what you do is you take a beam splitter and then you hit photons through that beam splitter. Let's say it is a single photon source. So single photon source meaning one single photon coming, then after a fixed time period, the second photon coming, and then after a fixed time period, the third is coming, and this time period is fixed, let's say 10 nanoseconds. So every 10 nanoseconds, one single photon is coming, and then you do this interferometry, HBT interferometer. So this interferometer has two detectors, and then light goes through the beam splitter. So only one detector can detect at a time, because if it is a single source, it cannot detect or click both the detectors at one particular instance. And you do these kind of measurements thousands times, millions times, and you create a probabilistic graph. You create some sort of probability, and then by doing that, you find out that your G2 measurement is going to zero. So this is how you could do that. I mean, I can try to show you. Let's say you have a, so suppose you have a beam splitter. Single photon comes from here, and then there are two detectors. So you go here. There is one detector, and then there is the second detector. And now let's say single photon pulses, single photon, equidistant pulses are coming. And what you try to do is you try to measure, this is your time t, and this will be time t equal to 0. And here you try to measure this G2, G2 tau or time. What is G2 is the correlation of the first photon with the second, then the correlation of the second with the third. So G1 is correlation of the photon with itself, then G2 is the correlation of the photon with another photon. What you try to get is something like this. And here this value maximum is 1, and minimum this value is 0 or something. So what you do is that you keep sending these photons. There is a machine called time tagger, coincidence counter, and then they will be click. Maybe this photon will come, it will click here. The next one will go, it will click here. The third one will go, it will click here. The fourth one will again click here, will not click there. So you can keep a record, and once you do that recording and do this time measurement, you will find some sort of statistics like this. So by doing that, it's called HBT interferometry. You can do that. How to ensure that one photon is coming, not many coherent photons. Yeah, this is what I said. Like if the see in the HBT interferometer, if coherent pulse is there, then this interval will not be equally spaced. It will be something like this, and then like this, and then like this, then this, and then this. And when you do the G2 measurement, your measurement will not be like this. It will be more like a straight line. It is actually more like statistics. So if you understand statistics, you will see that there are ways to find it out what kind of light it is, whether it is a coherent light or it is a subpoissonian, Poissonian, and there are other ways. You can actually also find out the rather than G2 function, just find out the photon statistics. That can also tell you which kind of light source this one is. Okay, so we stop for 5 minutes and then I will come back. Please write any questions if you have in the chat. I will try to answer. Um, okay, then see you in 5 minutes. Okay, so maybe we can start.
Yes, please, Baba. Start.
Yeah. So I hope now you understand that there is a problem in detectors, classical detectors, and we have this short noise. But actually, what we want is we want to measure below the short noise limit. So what are the options available? The first option is either we modify the light source or we modify this detection scheme somehow. As I already told you that there are some quantum light sources available, and these are called sub-Poissonian light sources, which shows statistics below the under root of average number. So the fluctuations are very less. They are equally spaced. Those sub-Poissonian light sources, either we create those light sources, then it is possible to go below short noise limit. One example is single photon sources. Another example is squeeze light. The second method is to do something with the detection technique. And one is called balanced homodyne detection, and there is also something called balanced heterodyne detection, but more or less they are the same. So let's go one by one and try to solve this short noise problem. So this is the second topic of today's lecture. So let's try to detect a single photon source. And remember, if you want to detect below the short noise limit, uh, produce a single photon source which maintains the anti-bunching. So let me tell you, suppose this is the single photon source we have, and equally spaced photon, no fluctuation or very less. And these kind of single photon sources you can create using NV centers, 2D materials, or um, single photon sources by quantum dots, trapped ion, and all that. How we measure? So when we do optical detection, we usually use a beam splitter, and then these anti-burst photon comes. Some will transmit, some will reflect, and then you have a detector. You will detect it. Look at this beam splitter. So what is a beam splitter? Beam splitter is roughly some material, some zinc oxide coating on top, or some glass material which is transparent, um, with back reflective layer of silver, something. It is a material, right? That has to pass through it to get transmitted. Suppose this was the anti-bunched light source, single photon source, light was coming, and you hit it with a lossy media. The problem is again the absorption process itself is a random process. So what this will do, the absorption will degrade the photon statistics. So they will not be remain anti-bunched, and some something like this will happen in output one, or something like this will happen to output two. So this is the degradation of the statistics, and now in these cases we will have more fluctuation, and the light will not remain, let's say, pure single photon source or anti-bunched completely. But what we have to keep in mind, we should not go into this regime where we have fluctuations which are bigger than the average number of photons square root. So if somehow you are able to maintain the statistics even after the beam splitter in such a way that you are below under root of n, then you can definitely measure below the short noise limit. So whatever I'm telling you, it is from the creating a light source side, like create a light source, make a light source which is already very good in terms of anti-bunching, and then even if some sort of statistics is loose or some bunching is there, still if you are under this particular regime, you can still create a light source which might have a G2 of 0.03 or 0.25, but below 0.5 people still consider it as a single photon source in community. The second option, again from generation of the light side, is create the squeeze light. What is a squeeze light? So suppose, again, if you want to work below short noise limit, produce a squeeze light in such a way that it maintains the squeezing. So I hope you have already studied all this squeezing of the light and all. So I will just go very superficially, not in too much of detail. Let's say this is some classical electric field. This is how we typically write it. The amplitude and the phase and the frequency of the wave and the vector, k vector, and the z direction it is propagating. The similar electromagnetic wave can also be plotted in a phasor diagram. So uh, the length of the phasor gives you the amplitude, and then this is the phase of the wave. Why we do that? So remember, the magnetic field is very small as compared to the electric field. So the electric field of the light is quite high, and magnetic field is divided by the C. So that is quite small. And it becomes very difficult to plot it in that way. So what we usually do is that we create some different coordinates. And if two things are 90 degrees to each other, we call them quadratures. So similar thing can also be represented in different ways, like x1 and x2. So again, this length of the phasor shows the magnitude, and the phase is represented by phi. So suppose we have a sine wave like this, and then when it's at 0, it will be a phasor like this. When it goes to 90 degree, the phasor will be like this. And when it is at some other instant, you just take the projection at x-axis and y-axis, and you will get the amplitude and phase. So that is just another way in classical physics to represent the electromagnetic wave. Now, another important thing is this Heisenberg uncertainty in distance and the momentum, and which is should be more
Vaibhav,
than h cut by
Dr.
2.
Vaibhav,
Yeah.
uh,
Yes.
your slides are not visible. So can you please go to presentation mode first?
Oh yes. Yes. Okay. Yeah.
Maybe please could you resume, because I could see the participants. They are not able to see the slides. You could just resume and quickly cover the
Uh,
slides.
is it visible now?
Yeah, it is visible. Perfect.
Okay. Should I go back to the previous slide?
I think so, but
Yeah. Let me see in the chat what people say. We have not seen since last 9 minutes. Okay. Yeah, so I will start again. So the problem statement is that we have a thing called short noise, and we are having. I hope you can see my screen now. Is it visible now? Okay. So we have this short noise, and we want to actually measure below this short noise. So there are some ways. The first way is you create some light sources which can do that, and the another way is that you create a detection scheme which can do that. But the main aim is to go below the short noise limit and measure there. I told you all the classical light source, lasers, LEDs, they all have problem with short noise because the photon, they come with some statistics, and this statistics creates a problem, which is noise. So which kind of light should I create? I should create a light which is sub-Poissonian in nature, meaning the fluctuations are very less. How less? They should be lesser than the root of average number of photons. And what are these sub-Poissonian light sources? One is called single photon light source, another one is squeeze light, and there are others as well. The another option is to do something with the detection, which is called balanced homodyne detection. There is another one which is heterodyne detection, and more or less they both are same. But by doing these things, we can detect below the short noise limit. So that is the another topic for today. Uh, so suppose you want to detect below the short noise limit. and somehow you have a single photon source. Now your aim is that the single photon source should maintain its anti-bunching. So how the single photon source looks like? It looks like this. The gap between the photons is equal. They are equidistant, meaning anti-bunch. No bunching, meaning 2, 3, 5 photons are not clubbed together. Who gives these kind of light sources? There are things like quantum dots. You can create single photon sources using them, or you can use 2D materials, silicon carbide, graphene, and all that can also give some defect state, and then from that defect state you can get single photon sources. SPDC process down conversion also gives you single photon sources. Now, when you go for detection, actually, what you do is single photon sources, light is coming, it hits a beam splitter, some light will transmit, some will reflect. And when you say beam splitter, this beam splitter will be some material. So maybe glass, zinc oxide, some silver coating, and then light has to pass through it. The problem is that we have this anti-bunch light source, then we have a lossy medium, then there will be absorption of these photons inside this medium. And these absorptions is random and they will degrade the statistics. So what happens finally, you see this light was coming in the incoming photons, and in the output 1 and 2 you see the light is no more perfectly anti-bunch, so there are some photons which got absorbed, and this creates problem. This again will give us fluctuation. So we can use single photon light sources and we can measure below short noise limit. What we have to remain in our mind is that we should not go into this regime where the fluctuations become too high. So we can measure with the beam splitter, but we have to remain that even after the beam splitter, the distribution and the fluctuation should be less than of average number under root, and then you can measure below the short noise limit. The another option is to create a squeeze light and maintain the squeezing. First you create the squeeze light, then you maintain this squeezing. This will also give you short noise limited signal. So how we do that? So I just give you briefly, because I know you have already studied all this. So electric field can be represented in this way. That is the magnitude, omega is the frequency, phi is the phase, and z is the direction where it's propagating, k is the wave vector. And one can write it in this way. Imaginary and real part of the amplitude, and then this phasor represent the magnitude, and this is the phase. That's another representation to show electromagnetic waves. But why we do that? The problem is that electromagnetic waves, that is optics. If you want to combine optics with electronics, you need to find out some way out, because in optics, the magnetic field is quite weak as compared to electric field. You see, you are dividing by 3 into 10 to the power 8. So the magnetic fields are quite weak, and if you try to plot both of them together in x and y axis, you will be in trouble in terms of scaling. So because of that, people create different ways to show a sinusoidal wave, and they create two different quadrature. They are related with each other with the magnitude again, but they just it's a different representation. And quadrature meaning x and y axis are quadrature, meaning two things which have a 90-degree of angle with each other, they are quadrature. So here also this is the phasor, that's the magnitude, and this is the phase. So it shows this sine wave. If the wave is here, meaning phase is 0, so this phasor will go something like this in this direction. If it goes here, meaning the wave has 90 degree of phase. So this is just another way of showing the EM wave. The another important thing is the Heisenberg uncertainty principle with momentum and position. You cannot measure them with precision. So if you measure one of them with precision, the another one will have a lot of noise or uncertainty in it. And if you convert that into quadrature, the equation becomes something like this. So there is three important type of quantum lights which you can measure below short noise limit. So I just give you brief examples. So first you have to understand this quantum harmonic oscillator and classical oscillator. So we all know this Maxwell's equation, how light propagates, propagation direction, electric field and magnetic field, all perpendicular to each other. This is a TEM wave. Energy is defined like this, and this is how we show this E field, right? But when we do quantum harmonic oscillator, this is how the energy comes out. So even when the no photon is there, zero, n is zero, then also we have some sort of energy. But classically, we don't say like that. If classically there is no light or no wave, there is no energy. But in quantum, if the number of photon is zero, then also we have energy. And that is called 0 point energy or the vacuum field. And the state associated with this is called vacuum state. So what is vacuum state? So if you plot that on a quadrature, this is how the vacuum state looks like. That there is no photon, meaning you are at the exactly 0, 0 location, but still there will be some sort of uncertainty in x1 and in x2 as well. And what will be the value? That will be half and half. So multiplication of x1 and x2 is 1 by 4. So those are the states where there is no photon, n equals to 0, right? That's vacuum state. What happens when n is not 0? Then let's say we have different states, coherent state, amplitude squeezing, phase squeezing. So let's first talk coherent state. What is coherent state? So again, these quadratures, I will plot it in terms of quadrature. So remember, these quadratures, you can tell whatever you want. You can say x1, x2. If you talk in terms of quantum mechanics, quantum physics, you say momentum and position. If you say classical physics, you say phase and amplitude. But this is just a way to represent electromagnetic wave in classical. In quantum is just a way to represent different state of light, whether something is coherent or something is vacuum state or something is amplitude or phase squeezed. Suppose I take a vector and amplitude and phase of this vector is uncertain. This we know from the Heisenberg equation. And this uncertainty will be something like this. What does it mean? That this vector not only can be like this, it can also be like this. So within this circle, I can also plot another vectors. So there is always uncertainty. And if you see the extent, this will be half. And in y-axis also, this will be half. And if you multiply again, this should be always greater than h cut by 4. This is how it looks like. So suppose in the quadrature, you are here, that is the coherent state. Because it's not here, if it would have been here, this is the vacuum state. So this is the coherent state. The red color shows the phasor. And exactly at this location, there is some sort of uncertainty. What is that? Actually, if you look at the wave picture, so the red color is the actual wave. Then what are these black dotted things? So you see, this is, let's say, time. And at this point, wave has 0 phase, here 90 phase. And this is the total amplitude. What you see here is that the amplitude is quite high. And also here the phase is not well defined. So you cannot really say what is the amplitude, whether the amplitude is this much or the amplitude is up to here. So there is some sort of uncertainty. And this is uncertainty in amplitude, and here we have uncertainty in terms of phase. And this is what you see here. This is one uncertainty, this is the second uncertainty, and the values will be half half. This is called coherent state. Now I will show you a video. So let's say this is how it looks like. So on the phasor, this phasor is rotating, and it's rotating, and here you see the wave. So it's just a representation to show the wave signal in a phasor diagram, right? This is how it looks like. Now you see that amplitude noise or uncertainty's amplitude is quite high. You don't really know what is the amplitude up to here or there. And it's similarly the case for the phase as well. Now suppose I do amplitude squeezing. What do I mean by that? Is is that I have reduced this dimension. So somehow I reduce amplitude, then definitely I will increase the noise in the phase. So if I reduce the noise in amplitude, the phase noise will get increased. And now if you see, this is how it looks like. So if I have created a wave like this, then what happens is that, for example, at this point, very precisely you could say what is the amplitude. So this is the amplitude very precisely, but you cannot say whether the phase is this much or the phase is this much or this complete thing is the phase. Like, what is the phase? So phase becomes uncertain, and that is called amplitude squeeze light. Now the question is how to create these kind of light sources. That is not the topic for this lecture, but there are ways to create these kind of light sources using nonlinear crystals, NDR lasers, and BBOs. You can create these kind of squeeze lights. So there are different kind of squeezing. One is coherent squeezing. I told you, here we have photons. It's not like we don't have photon. That is only the vacuum state. And we have uncertainty here. That is coherent state. If we can measure amplitude nicely and we have uncertainty in phase, that is the amplitude squeezing. We have squeezed the amplitude. So this axis is squeezed and this axis is long. And the third one is phase squeezing. So this axis amplitude is quite long and the phase is squeezed. So there are these three typical squeezing, light squeezing. And if you are able to create these kind of light sources, then you can measure and you will not get into any trouble because of the short noise, because somehow you have reduced the noise in one of the quadrature, so you will not get into the trouble of short noise. And anyways, these kind of signals, they have very less fluctuations. Their fluctuation is smaller than the average number of under root, so this will not be any problem. Now comes the detection part. So okay, suppose I'm not able to create something like coherent light or something. I have created a squeeze light. Let's say I have a squeeze light. Now, how do I do uh, quadrature detection and all that? So for that, what you do is you use balanced homodyne detection. So what we have here, this is a 50-50 beam splitter, and one light comes from here, the second light comes from here. So whatever is green is the input, and then whatever is the red is the output light. So this light and this light, they will come, they will interfere, and then one light will go here, transmit, plus reflect. So this will get transmitted, this will get reflected here, and on this one, this will get transmitted and this will get reflected. And then there will be interference here, and then you get two parts, A3, A4, and then there are two detectors. This is the basic homodyne detection. People also use it in optical communication and electrical and electronic communication. Suppose I have a signal which is psi, and this signal can be amplitude squeezed, phase squeezed, vacuum signal, coherent light, it can be anything. On the other side, I have a signal called beta. We call it coherent state or local oscillator, or we call it a laser. Same thing. In the end, if you are using quantum optics, just put a laser here, classical laser. And if you are using electronic circuits also, then also you call it local oscillator, meaning you also put an oscillator here. What is important in homodyne detection is that the frequency of the signal and this local oscillator should be same, and amplitude of this local oscillator should be very high. So what is your input state? So your overall input state in terms of classical mechanics is the tensor product of beta and psi. So you do the tensor product, that is your total input state, which will go through this beam splitter, and then there will be interference at the beam splitter. So what we can do is actually we can, by using this homodyne, we can calculate the quadratures. And if we are able to calculate the quadrature, we can tell what was the light, whether it was the vacuum light or it was the coherent light or it was the phase squeeze, whatever. Um, So how should we do it? What will happen is that once we apply these signals, this input signal, there will be current associated. And we know that current is proportional to the incident light, which is proportional to the photon. So if we know photons, how they operate on a beam splitter, we can find out what current is I3, what current is I4. And there is a particular math which one can do. And finally, what you find out that if you take I3 and I4, these two current, and if you subtract them, I3 minus I4, which can be written like this will be equal to something like this. What is this value? So this is actually, you see these bracket, that is the mean value, and that is the one quadrature. X is the quadrature which is applied on state psi. So state psi, what was it? This was a signal, right? So if finally we are able to measure I34, which is the difference, if we measure this, then actually if we divide this by beta, then we can actually find out this X quadrature value. So difference in the photocurrent gives you average value of the quadrature component X for a phase angle phi plus pi by 2. What is phi? Phi is the phase difference between this local oscillator and the signal. So actually it's in our hand. We can change phi, and then for different phi we can keep calculating I3 minus I4. So by doing that we will get uh, something. I will explain you. But I hope you understand how the mechanism works. So we give two inputs. One local oscillator. This is roughly a laser, a very high intensity laser. Why high? Because this signal will be very small. Let's say if it is a coherent state, amplitude squeeze, we are talking about 3, 4, 5 single photon, 2 photons. So this will be very low intensity. And we want to increase the intensity. So this beta, which is the amplitude of your another local oscillator, the signal will be multiplied by beta and it will be enhanced. So we can also enhance the boost, we can boost the signal. That is the another advantage by putting this local oscillator. So there is a very good paper in Nature in 1997. I will encourage you to read this paper. What they have done is that they have used the same scheme and they have done the homodyne detection. So I will go very slowly here and try to explain things. The very first state here, this is a coherent state, right? You look here, this is y-axis, that is the noise current. So they have measured I3 minus I4, which I just showed you. And if you look here, you see that amplitude and the phase both have some sort of noise and uncertainty. So this is uncertainty, this is the phase uncertainty, right? And this particular this particular axis is phase quadrature. This is the amplitude quadrature. If this same Gaussian would have been here, we will call it vacuum state. Since it is away from this location with the phasor, so this phasor with the phase like this, and you plot this Gaussian, that this is the coherent state. The second is the phase squeezed light. So if you see here, it will be very difficult for me to tell what is the amplitude, but it is very easy to tell what is the phase because this phase noise is very low. So that is phase squeezed light. Now you see in the phase quadrature, there is very less fluctuation here. But in the amplitude quadrature, the fluctuation is quite high. Now, similarly, if you see this is the amplitude squeeze light. So in the amplitude direction, there is very less noise. You can also measure amplitude very easily. But in the phase, you will have hard time to tell what is the real phase. And then finally, that is the vacuum state. So that's the Gaussian is at this location, and this is the vacuum state. So what they have actually done, they have created, if you see this graph on the x-axis here, they have a quadrature amplitude. So amplitude is here, which was in my case, this was the amplitude here. And the phase 0 to 2 pi is shown on this axis. So the phase is shown here. What you have to do is that keep changing the phase of your oscillator and keep calculating I3 minus I4 and do it multiple times and try to plot, these density diagrams. People also call it phase space distribution or Wigner distribution. So uh, this is amplitude. So amplitude, you know that local oscillator, I told you, will have very high amplitude. So fix the local oscillator that it has an electric field somehow like this, and the peak amplitude is, let's say, 10 here, and the minima valley is minus 10. Since your actual signal will be having very low amount of intensity because it will be some vacuum noise or something else, don't worry about that. So we fix the local oscillator, its magnitude. It is just an oscilloscope, right? So, or some laser. So fix the magnitude. Let's say peak magnitude is 10. And then what you do is change the local oscillator 0, then 0.1, then go up to pi, and then also go up to 2 pi. So 0 to 180 degree, keep doing it for 35, 36, 37. More precisely you do, better Wigner function you will create. So that is nothing but a Wigner function has been created by giving different values to the oscillator. So I told you here, this is this phase. So that is the phase difference between the signal and your local oscillator. You can keep changing this, just keep changing 0, then 1 degree, then 5 degree, 7, 10 degree, 20 degree, go up to 360. And for each pi, you will be getting current and then also plot that current. And just by doing that, you will be having this kind of diagram, which is all different sort of light can be traced back just by looking at the noise signal and the Wigner distribution. And you could even see that this is actually a wave. If you look like this is actually the same wave. It's a wave. And here you also see that usually the probability was roughly the same in case of coherent state, but as soon as you go phase squeeze states, for some particular cases, the intensity or the probability to find something goes very high. These are the instances where you really have your signal, which is getting interfered by your local oscillator. So actually these are something called beat notes. So at the beat note, you will get these kind of distribution. And again, you could also see, I mean, they are also similarly, they are waves. Um, so how people do it in real life? So let's say there is some ND-arc laser, then there is some fiber cavity. So first, create a squeeze light. So let's say whatever part is here, this part is used to create squeeze light. Then this squeeze light comes here, and this is called signal, right? This signal here, right? And this signal goes to this beam splitter. Then we have something called local oscillator, and this local oscillator is also going and hitting this beam splitter. And then we have two detectors, one here, one here. Whatever comes out of these two detectors, we will subtract them, and then we will apply some low pass filter. So homodyne detections actually happen here. Whatever schematic is here is just to create a squeeze light. So we have frequency of signal and frequency of local oscillator. I told you we try to keep them as close as possible for homodyne, and for heterodyne they will be different. Here the amplitude will also be quite high. Now when I say the interference will happen at the beam splitter, I mean to say that these two frequencies will get created. What does it mean? That you have one very high frequency, and suddenly it drops, and then it goes again up, and then it drops again. And then you could see that you have the second waveform, which is on top. So this omega 1 minus omega 2 is this one, and this high frequency is this one. And what you do is you take a low pass filter, meaning only low will pass. So this will pass, and you try to pass this particular signal. So when you do this interference pattern, you create both the signals, high and low, and you only pass the low signal. Um, then by detecting the difference into the flux, So here what you have is that you have the difference, because this is actually will finally converted into the current, and this current depends what kind of signal was coming. So this you do electrical signal which provides you this x theta, this quadrature, which I told you already, that there is a formula which can calculate I34 equals to beta times quadrature value. And if you plot this, and theta is the relative phase between the oscillator and signal, and you try to plot multiple values, local oscillator, keep changing its this local oscillator's theta, and then try to get a probability distribution for different theta values, and finally you create a Wigner function distribution. And by that distribution, you can tell what kind of signal was present here. Uh, so this diagram was available in that paper, and by reading that paper, a lot of your concept to how to create squeeze light and how to do these homodyne detection will get clear. So with this, yes, I would like to conclude, and yes, if you have any questions, please feel free to drop them in the chat. Yeah, I think it is this paper, measurement of quantum state of squeeze light. I can just copy paste in the chat.
Okay, Dr. Vaibhav. It was nice talk. Somehow there was some intermittent network issues, I
Yes, sir.
suppose. Yes. Yeah, there
Yes,
is
sir.
one
Yes,
new
sir.
question.
Okay, squeezing and tunneling. I I think I don't understand what someone I'm squeezing. So tunneling is a different phenomenon as compared to squeezing. Um, so squeezing is also actually this happens in, let's say, gravitational wave detectors. You will also find squeezing. Um, but tunneling is completely, I mean, it is also a quantum phenomenon. Also, recent Nobel Prize and all went towards this direction, but it is different than squeezing. Or maybe if I'm misunderstood, please correct me. But I hope, I think it is something else. So the nature of vacuum fluctuation is actually Gaussian. They are usually Gaussian in nature. Um, the nature of the vacuum fluctuation surrounding single photons.
Yeah, you gave some
What is the
experimental flavor of squeezing of light, so there are some more queries.
Yes, actually, the idea is to give you experimental idea how squeezing is done in terms of experimental sense, and how you measure that, and how finally these Wigner functions are plotted, and also regarding short noise limited systems. So briefly, you can understand that, okay, if you have somehow created the short squeeze light, you can actually measure things below short noise limit. So then you are not really limited with the short noise.
Okay, I think not any more query. So I thank you, Dr. Webber, for such a nice session. And these topics were theoretically discussed sometime during some lectures. But yeah, this experimental flavor was really nice. And
Yes, yes.
yeah, so okay, so thank you once again. And yeah, this day, and we both had very learning kind of Sunday. Okay.
Thank you, sir. Yeah, thanks a lot.
Yeah. Okay. So thank you everyone, all the participants. Now I think we'll stop the session. Thank you so much, sir. Bye.
Thank you, sir. Okay.
Yeah.